AI training is getting weirdly more predictable and more efficient at the same time. One result shows that you can overlap rollout, scoring, and learning in post-training without losing accuracy, as long as you respect how stale data behaves under different KL objectives. Another shows that for test time compute, the best coding model may only need one extra refinement loop, not more. And the third turns GRPO from a black box reward curve into a dynamical system you can actually reason about, which means better tuning, fewer surprises, and a lot more control. Let's explore the first paper, Async OPD, How Stale Can On-Policy Distillation Be? Async OPD, How Stale Can On-Policy Distillation Be? Is the first systematic study of staleness in asynchronous on-policy distillation for large language model post-training using a Qwen 330B, A3B Instruct 2507 teacher, and Qwen 34B base 1, 7B, and 8B students on deep math. The paper shows that KL direction fundamentally changes the stale data problem. Forward KL is teacher-weighted and stays comparatively robust as rollout lag grows, while reverse KL is student-weighted and degrades faster. For reverse KL, the strongest correction is not a complex asynchronous RL surrogate such as decoupled PPO or M2PO, but a simpler OPD-specific estimator that recomputes the advantage of theta at learner time and removes PPO clipping. The authors also show that stale top K teacher caches are support mismatched, whereas sampled Monte Carlo reverse KL remains correctable by old to current importance sampling. Increasing the number of local samples from 1 to 64 sharply reduces variance, with fixed prefix variance falling to 0.0149 of the one sample baseline. Building on these estimator choices, Async OPD overlaps rollout, teacher scoring, and learning in a fully asynchronous pipeline, and improves throughput by 1.6 times to 3.8 times over strict synchronous training, while maintaining comparable final accuracy on AME 2.4, AIM 2.5, and AMC. Let's explore the second paper, LoopCoder V2. Only loop once for efficient test time, computation scaling. LoopCoder V2, developed by the Beihang University and iQuest research team, studies how parallel loop transformers saturate under different loop counts for test time compute scaling. The paper trains a 7B coder from scratch on 18T mixed text encode tokens and shows a sharply non-monotonic effect. The two-loop model is the best operating point, lifting SWE-bench verified from 43% to 64.4% and multi-SWE from 14% to 31%, while 3 and 4 loops regress below the baseline. The core technical explanation is a gain-cost trade-off. Cross-loop position offset enables near single-pass latency and nearly constant KV cache memory via shared first-loop cache plus gated sliding window attention, but it injects a fixed positional mismatch at every loop boundary. Internal diagnostics show that Loop 2 carries the largest hidden state update, the largest interloop attention shift, and the peak effective rank, whereas later loops become oscillatory, redundant, and increasingly dominated by the offset cost. On broader code and agentic benchmarks, the two-loop model reaches 84.1 on human eval, plus 73.9 on multi-PLE, 46.1 on big code bench full, 35.4 on live code bench, and 40.1 on SWE-bench verified, demonstrating that a single extra latent refinement loop can outperform far larger models when the loop count is chosen correctly. Let's explore the third paper, Predictable GRPO, a closed-form model of training dynamics. Predictable GRPO, from researchers at Nutanix and Unsloth, turns group relative policy optimization from an empirical curve-fitting exercise into a closed-form dynamical model. Under a single mean field assumption, the paper reduces GRPO to a stochastically forced, damped oscillator whose mass, damping, and stiffness are determined by optimizer hyperparameters and one measured curvature scale. Momentum supplies inertia, stale policy refresh erodes damping, and group size G acts only as noise temperature. This reframes the widely used saturating reward law as the overdamped limit of the second-order system, while the retained inertial term explains the slow start phase that a single exponential cannot capture. On GSM 8K, 3 open-weight models, Nemotron, Mini, 4B, DeepSeek, LLM, 7B, Chat, and DeepSeek, R1, Distill, Qwen, 1, 5, B trained with GRPO at G equals 4 and G equals 16 are fit by the three-phase law with R2 is greater than or equal to 0.91 and the deterministic trajectory is approximately G invariant, while stationary fluctuations shrink as 1G. The model also predicts a refresh interval stability threshold, Kitterkref is greater than 1-, and a monotone to oscillatory transition. These are confirmed in an exact softmax bandit reduction with P equals E pi theta R closed exactly using a single prompt with 8 completions and a measured stiffness of 0.12. Out of distribution, GSM-AK train policies transfer to 8 math benchmarks, including GSM+, MetaMath QA, OpenMath 2, Numina Math, Math 500, IMO-bench, AIME 202.6, and HeyMMT 202.5, with the strongest gains near the training distribution and much weaker gains on competition-level tasks. That's a wrap on today's AI paper highlights. Thanks for watching.